has to, like, the total has to be zero.
Oh, yeah, just their thing.
Yeah. So then MV, they don't have to be the same, or they don't have to be, but the components have to be just like MV, D sine theta, A sine theta, negative, B.
But there's no,
Yeah, it's A. I don't know what this is on there. Know this. Know this. You don't have to be circle. So then, we solve for theta. Like this one, in this equation, we don't know cosine theta, either the cosine.
Okay,
But the theta one is calculated by this.
so
Yeah.
usual straightforward strategy here. We talked about this last time. Draw things, set up a coordinate system. I'd already done that since we talked about it last time. Wrote down a list of knowns. Didn't like write down a list of unknowns, so it's good that somebody asked what is it that we actually need. And then it's simply applying our conservation expressions. So let's do this for kinetic energy to begin with. We have 1/2 mass of A times dA1 squared. That's the total kinetic energy before the collision. Object B is initially at rest. And then we've got two objects moving after the collision, so BA2 squared plus 1/2 MB dV2 squared. Scalar quantity, so no vectors anywhere in there, pretty straightforward. Hope everyone's okay with that. In terms of looking at momentum conservation in the x direction, so a little bit of use of components here, but the initial state is pretty straightforward. So we've got the mass of A times the velocity of A. That's all we've got in our initial condition. B is initially at rest. And you see I've not put anything about x direction here because I've implicitly set up my x-axis along the direction of the initial velocity. So that's easy enough. Maybe I'll ask for your help on this part and the similar part on the last Py conservation. What do I need to worry about on the right-hand side for momentum in the x direction after the collision? Yeah?
You have to use the x component of the velocity.
Okay. So you want to help me out with the first one? Let's worry about A.
MA times VA cosine of theta A.
Yeah. And plus, let me do this bit for you. It's pretty straightforward. VB cosine of theta B. Both in the same direction, which is to say in the positive x direction. So they're coming in both with positive signs. What about y conservation? What's my initial momentum in the y direction? 0, right? So while object A is moving, it's moving solely along the x-axis, so that's why making that the choice of the x-coordinate makes a lot of sense, makes the algebra much easier. Okay, we're almost done. Might need to be slightly careful here, however, with signs. So what do I need on the right-hand side for the y momentum after the collision? Yeah.
Or if you make the theta negative on A, either way.
Okay.
Plus MBB.
Okay. So, all right. So a couple of ways of handling this, right? First off, note that, I'll get to your question in just a moment. Note that the way we've drawn this, we're expecting, and in fact, not just expecting, but we kind of mentally deduce that if one of them heads off, let's say, in the plus y direction, the other one must be heading off in the minus y direction, just because of momentum conservation. So the question of how you handle the sign is a little bit up to you. You might, if you were kind of treating both angles as shown to be positive. You might say that you're going to take care of the sign by putting the component of the B velocity as being positive and the component of the A velocity as being negative, simply because it's in the minus y direction. Or indeed, yes, you might have defined your angles as maybe the convention would have it, defined with respect to the positive x-axis. And so in that case, you would worry, or not worry, you make sure that you define this as being negative, and the negative would come for you in that case, okay? But whichever way you're choosing here, make sure you're careful about the signs, S-I-G-N-S. Yeah?
Does initial versus final not matter since you didn't like put ones or?
Oh yeah, thanks for telling me I need to put in my 2's. Yep. So you can see how easy it is to start using subscripts here when we've got so much going on. Yep.
Set it up as just all of them positive, and then one of the velocities will come out to be negative, and then come out to be positive.
So in this case, no, you definitely need to embed in there, well, you really want to embed in there that you know one of these is going upwards and one of them is going downwards. So I would say, since you do know that in this case, better just put it in there and just work with it, okay? All right, so fairly straightforward, just for completeness. As usual, it's algebra at this point. Let me try and do this right across here. So in the case of the kinetic energy conservation expression, simplify things, drop some halves. So I would have in this case the velocity of B after the collision. Square of that is MAVA1 squared minus MAVA2 squared over MV. We know all of these things, so it's plug and chug, and it turns out that this is 4.5 meters per second. Okay, so that comes right out from our kinetic energy conservation. And then in terms of our momentum conservations, the way that I found kind of easiest to solve this, but you can do whatever you prefer, just one thing to keep in mind, a kind of trick, if you will. But again, you can solve this in whatever way you wish. Now that we know VB2, we have two unknown angles, two equations, so it's certainly solvable. I happen to do this by just looking at sine squareds of an angle plus cosine squareds of an angle equals 1. But again, it's not necessary to use that. Whatever substitution you like, and it turns out in this case that theta A and theta B, if I've got this the right way around, I get 36.9 degrees and 26.5 degrees. Let me just check that I got this the right way around. Let's see. I actually did not. It's the other way. Okay, theta B, theta A. Okay, so both of these angles defined as positive, but obviously drawn as shown, so theta A is below the plus x-axis. Questions? I know it's a very sort of uninteresting example, but just want to make sure you're okay with the setup of these three equations of conservation of kinetic energy and momentum. Oh, thank you. Yep. So it doesn't do me any good to rush on these things. So the velocity is 4.5 meters per second. Yeah. So what I would have done in this case is, let's see. So I guess here we've got an expression for sine theta A. I would also have got an expression from here for cosine theta A. And what should happen if you apply that trig identity? It doesn't maybe look super straightforward. if I simply get the expressions for those things and I square them, what I should have in there is also, I should have sine squareds plus cosine squareds of the other angle, so that should drop out, and I should just get it in terms of masses and velocities. So I think that's what I did in this case, but of course you can solve this in whichever way suits you best. Okay, good? All right, so let's turn our attention to the slightly more interesting case of mass varying systems. And pretty much the only scenario we're going to look at here is for so-called rocket motion. And this is a little bit of a weird derivation. I'm going to go through it. And of course, since we've got a varying mass, you can imagine we're going to be using calculus. So let me call this rocket propulsion, and we're using momentum conservation. Okay, so you've heard me say a few times in the past couple of weeks, our use of energy conservation, or recently momentum conservation, allows us to handle situations where we might, in principle, also be able to solve problems with Newton's laws. Okay? Newton's law, if you think about it, however, we are dealing with forces acting on masses, and up until now, we've always been dealing with scenarios where those masses are constant. So as soon as we're in a situation where masses are changing, which they are in rocket propulsion, because as I've talked about in the introduction, every instant that I'm firing my rocket, I'm ejecting some mass in the form of exhaust gases out the back of my rocket. So I've got a continually changing mass from my rocket. So Newton's law is not going to help us in this case. So I'm just going to write that as a footnote. Okay, so the mass is continually changing in this case. All right, so let me draw a cartoon to get us started here. First thing I want you to be aware of, because I'm going to be talking about our rocket once it's essentially in free space, empty space. So to a large extent, it's immune to any external forces. We're going to ignore external forces. So no external forces. Draw a little bit of a cartoon here, showing our rocket kind of at a certain initial time, and at some fractionally later time. Okay, so come down below the handle on the chalkboard. We're going to talk about at some time t, and at a later time t plus dt, so a small time interval later on. Okay, stylized rocket here, and we're going to start off with an initial mass and an initial velocity. Moving from left to right in my chosen coordinate system, I'm going to pretty much ignore the coordinate system right off the bat, but let's say this is in the plus x direction. And then an instant later, time delta dt has elapsed. Here is my rocket again. And this is where I'm going to be starting to be slow and careful. Okay, first thing that is conventional in this analysis is already kind of slightly perplexing. But I'm going to define the new mass of the rocket at this time interval t later as m plus dm. Okay, now as soon as you think, when you see that, you might say, okay, mass is not increasing, it should be decreasing. So the only way I can maintain that is to say that dm is negative. Okay, so a little bit of a weird choice to begin with, but it's fine from a point of view of logic. So we're going to claim that the mass has changed from m to m plus dm. And again, keep in mind that dm is by construct here, it's negative, right? Now, if a rocket's doing what it should do, velocity here has changed a little bit, and it's now plus v plus dv. So a little bit of an acceleration. We're moving from left to right with v plus dv. And now what I'm going to try and represent on here is the exhaust gases that are being shot out the back of the rocket. So these exhaust gases, of course, carry some mass. And again, slightly confusing notation here. I'm going to write the mass that's carried by the exhaust gases in that minus dt as minus dm. Okay? Now, again, I claim that dm is defined as negative, so minus dm is positive. At least logically, it makes sense. Here, it seems like a totally weird thing to do. So, mass has changed. Some of the mass is being expelled as exhaust gas. The amount is dm. The sign is a weird convention, but at least it's logically consistent. And I'm going to worry about the velocity of these exhaust gases. And I need to make a comment about this. I'm going to call the velocity of these exhaust gases v prime. Okay? So, first thing to write here is the velocities are measured in some outside external inertial reference frame. So these are velocities as perceived by some independent outside observer here, okay? So in some outside inertial reference frame. I will also make the comment here that while the analysis is exactly the same as in our Sears textbook, the notation I'm using is a little bit different, so hopefully that's not going to confuse you. Again, the actual analysis is the same. All right, so there's the setup. I've defined initial masses and velocities. I've defined final masses and velocities, albeit with this kind of funky definition. What we should expect now is that momentum conservation applies to this situation. So we're going to apply momentum conservation, then we're going to do a little bit of trickery with relative velocities, coming back to something we learned about probably in third class this semester. We're going to do some manipulation, and we're going to get out a useful expression, a workable expression that will tell us something about how to design rockets efficiently. So it's going to look slightly strange for 5 or 6 lines. Don't worry about it, it's the end result we're after. And I will not ask you to repeat this derivation, but you should follow along, obviously, so you know where it comes from. Okay, so first off, we can only apply momentum conservation if our system has no external forces. We've claimed that it is. So now we're going to apply momentum conservation. Usual way. So P initial equals P final. So let's write this down. My initial linear momentum is just the mass times the velocity, pretty straightforward. And then on the right side, again, pretty straightforward, though the notation is possibly slightly weird. Minus dm times e prime. So just take a look at that and make sure it's consistent with everything I've told you so far. Clearly, a standard expression for momentum conservation. On the right-hand side, we're taking account of the differential changes in mass and velocity over the small time interval. I've got the opposite, or the relative momentum here, being like this. So I've got minus dm times v prime, and again, v prime is the velocity measured in the outside person's reference frame. All right, so now let's just take a quick look at using relative velocities. Okay, so just follow my notation here. Again, this is different, I think, than what's in our textbook. So let me write this down and explain my subscripts. So R corresponds to the rocket frame. F is some inertial external reference frame. Remember, inertial means non-accelerating, and E corresponds to the exhaust, the rocket exhaust. So R is the rocket relative to some frame we're about to talk about. E is the exhaust relative to some frame. And we're talking often about our inertial reference frames here. So does this make sense? Velocity of the rocket with respect to some inertial reference frame. And remember, if this is to work out, we better have our target variables kind of on the outside of the pairings here, and the same reference frame in the middle. So this is the velocity of the rocket relative to the exhaust, and you might think that's weird, but you'll see why in just a few moments. The velocity of the exhaust relative to the inertial reference frame. Okay, yeah?
What are the units of dm?
Just mass, right? Just a change in mass. Just as with v would just be a change in velocity. Okay. All right, so with this, we're going to recast this in terms of some of the things that we know. So v plus dv, that's the velocity of the rocket in the reference frame over here. So this is now the relative velocity of the rocket and the exhaust, hopefully I'm getting this right, plus v prime, the velocity of the exhaust in the external reference frame. Okay, so this is the relative velocity. You can tell I'm also pausing here because I find I need to check this at every step. So recasting this, just rearranging this. And now what I'm going to do is plug this into my momentum conservation. So I'm going to plug this into there. Now there's a fairly long expression. So let me see if this makes sense. So it's taking that and plugging in a few variables and also expanding cases where I've got two parentheses multiplied by each other. And get this all on one line. Didn't quite make it. The relative velocity times dm. Okay, let me step back here and make sure I'm doing this correctly. All right, momentum conservation, our usual way of looking at relative velocities. In a couple of cases measured with respect to an inertial reference frame, and then one relative to the other. That remains this one. So that's fine. Substituting, I get this. I'm going to substitute that into there. And then do the multiplication of all of the terms, okay? So this should be what I get. Yeah?
A good question. Why is the velocity of the exhaust a constant? Like you were saying, that's not a constant.
So we are imagining, in this case, let's see, the velocity. Why is it constant? I guess it's sort of a built-in assumption that our rocket is firing with some constant power, right? So until the fuel is exhausted, it's simply shooting out the exhaust at some constant speed. Remember, this is just over a differential time interval, okay? So it's certainly true that it's being ejected at a certain speed in that time interval. I think what you're asking is what happens as the rocket continues firing for finite amounts of time. And indeed, then it's going to change. But that's why if we use this differential notation, it should be fine in this small time interval. And yes, over time, it is definitely going to change from the perspective of the outside observer. What it presumably is not going to do is change with respect to the rocket itself, okay? So that's the implication of constant power. All right, so bear with me and then we'll get to the answer and then, yeah, go ahead.
Can you explain how you got the equations for v plus dv and then v prime?
This one?
Right.
Yep. So this is simply this. So that's our standard relative velocity expression without putting in any of the variables that I've defined for this particular case yet. So this is just saying that the velocity of the rocket relative to the outside is the velocity of the rocket relative to the exhaust plus the velocity of the exhaust relative to the outside. It's a slightly weird thing to do, but you know it's correct, right? So that's our standard definition for relative velocities when I've got, in this case, two objects moving. You don't look.
I was asking about the equation under that.
Yeah. So I just want to make sure you got
okay,
this to begin
right,
with.
yeah.
Okay? So then here, we've got the velocity of the rocket relative to the outside frame. We're applying it to this. And then I'm simply saying that this is now, I'm going to define this as now the velocity, I could have kept RE, but what I mean is the velocity of the rocket relative to the exhaust, so the relative of these two things. And then V prime is simply what I defined initially as the velocity of the exhaust in the outside reference frame. So it's simply a change in notation from our generic velocity addition situation to the variables that we're using in this problem.
So then that arrow, like in the diagram of v plus dv, encompasses like that v prime.
So this is the velocity of the rocket observed by an external observer. It doesn't know anything about this. So this is the velocity of the exhaust for an external observer, right? So velocity of the rocket from an external observer, that's this one. The velocity of the exhaust from an external observer, that's this one. So there's no connection point yet between these two, but the connection comes here.
Okay.
Yes, no, not really, kind of?
Yeah.
Yeah.
Would velocity of exhaust with reference frame to the rocket be negative? Like not like in the equation, but like the value would be negative.
So the velocity of the exhaust relative to the rocket is presumably negative, that's right. But here I'm only looking at it from the outside world. Okay? All right. I can see this is not working so well. Let's get to the end and then we'll come back and see if it makes any more sense. All right, so I've taken these variable definitions. I've used relative velocity to recast them in these terms. And again, you might ask, why am I going through all of this? Well, we're about to get to something useful. So I've opened up all of the parentheses here. And of course, there's a bunch of things cancel. And let me quickly put those in here. And so what drops out of this is the following. Minus V relative to M. A couple more lines and then we get something physically useful out of this. And then I'm going to go back and talk through it again because it's clear I have not done this well. Just make sure you're okay with the cancellation of terms that's on the bottom of the board to my left. Now we've got an expression that is just in terms of sort of differential changes in velocity and mass, but I'm going to now divide by dt. So I get this. And dv by dt equals minus v relative m by dt. And so I'm going to now define this. So This is a positive rate of fuel consumption. And again, we're moving towards something that may have some actual relevance for somebody who's designing a rocket. So if we define this, and finally write the following. I'm going to do this and then we're going to talk. So mass times the acceleration, that's this guy, is